What up, mathletes? Good afternoon. Woo! All right, so we're going to talk about our last little bit of transformations, and so I want to talk to you guys about that. The first one we're going to talk about is rotational transformation. It says the figure below has a point marked with a large dot. The first rotate the figure 90 degrees counterclockwise, right? So if a clock goes this way, counterclockwise will go this way, right? Against the clock. Then give the coordinates of the marked point in the original figure and the final figure. Before we answer this question, I'm actually going to walk you through using this as an exercise. So I want everybody to look at this point right here. What do we have? We have the point -7, 1. So it's -7, 1. Okay? So write that down on a piece of paper somewhere. And we're going to roll with it. So we have -7, 1. I'm going to write that down. Boom. That's our original. -7, 1. And then I'm going to go counterclockwise 90 degrees. What's our new point? Well, let's look. It's now -1, -7. Go ahead and write that down. -1, -7. That's for a 90-degree rotation. Don't worry, I'm going somewhere with this. You'll see it. Just trust me. Now I'm going to do it 90 more degrees. So now it's a total of 180-degree rotation. You see that straight 180-degree arc right there? And what's our new point right here? It's now 7, -1. Write that down. 7, -1. And then last but not least, I want to do a 270-degree rotation and see where we're at. We're now at, and again, this is counterclockwise, so we're now at 1, 7. Okay, so let me walk you through what just happened here. Notice I have these written down. This is for counterclockwise. You want to label this in your notes. By the way, this is a good time to remind you, what is your learning target from yesterday? It was, I will use transformations to manipulate figures on a coordinate plane, which is what we're doing right here. So the first thing we started off with was -7, 1. That was what we started off with. And if I were to, and then we went to 90-degree rotation was -1, -7. 180 was 7, -1. And our 270-degree rotation counterclockwise was 1, 7. Well, what if I were to call -7x and 1y? Well, think about it. For a 90-degree rotation, do you notice how our x value became our y value? So it's like I put x over here, right? Our original x. And our y value kind of switched into the x value, except it became negative. So it was the negative y value. And it turns out that's how it's going to work every time. As you work with these rotations, anytime you're going counterclockwise, you take the original coordinates and flip them and negate the y value, and that's going to be the new coordinate of your 90-degree counterclockwise rotation. In the same way, let's look from the original. The x values seem to stay the same, just get opposite. So it's going to be a -x in the x coordinate. The y value is also a negative, so it's going to be -y. So it's like we just took our original x, y, and did the opposite of both. That's it. And then our last one, our 270-degree rotation, it looks like this time we took the y and put it right in the x, so just normal y there. And then we took the x, put it in the y, but the opposite of x, so -x. And this will help us later on do shortcuts of doing rotations where we don't see the shape and we don't have a fancy slider thing that we can slide it, but we can immediately go, all right, if my original was -7, 1, and I'm doing a 180-degree rotation, I know I'm going to take my x, y, and I'm just going to make each coordinate opposite, and it becomes 7 and -1. So we can just change it that way, all right? So make sure you have this written down for counterclockwise. We're going to do one for clockwise as well. But there you go. Pause this if you need to. I'm going to go back to the other screen. Okay. But nevertheless, in this one, what is it asking for? And and if you're wondering why didn't I do a 360 degree, it's because it's going to line up right on itself, right? So again, 90 degree, line it up right on. We just went 90 degrees right there, and it went from -7, 1, to -1, -7. Let's check our answer. Oh, I right-clicked. My bad. Correct. Look at that. Boom. Awesome. Now I would like to check out problem 21. Just kind of doing examples that are going to get us through all the information we need. Draw the following triangle after a 90-degree counterclockwise rotation about the origin. So it's counterclockwise. All right. So I'm going to write down the 3 coordinates right here, okay? So number 1, we have the coordinate of the vertex of this triangle, which is 2, -1. I'm writing these down, and we'll look at them here in just a second. I have the coordinate of this vertex right here, which is 5, -3. And the coordinate of this vertex is 4, -5. And let's remind ourselves, looking at the counterclockwise rotations, we know, let me move my picture out of the way. We know that if I, how far am I supposed to rotate? I got to pay attention to the problem, don't I? 90 degrees. We're going just 90 degrees, okay? So I know that a 90-degree rotation is just going to flip my values. So my y and x are going to switch places, but I'm going to have the opposite of y. So if my x and y are going to flip places, I know I'm going to have 2 go over here. And what's the opposite of -1? It's +1. Again, my x is going to go to the right, and the opposite of y is going to go left, which is just +3. Same deal right here. X is going to go to the right. Opposite of y is going to go left, so 5. So let's try this out. We're going to put our new coordinates in. They should be 1, 2, 3, 5, 5, 4. Make sure you write this down in your notes, and we're going to check this out right here. Let's see what happens. All right, let me draw my points. So it said I should have the point 1, 2. 1, 2. And I should have the point 3, 5. 3, 5. And I should also have the point 5, 4. 5, 4. Let's connect those lines and see what we get. Certainly looks like the same triangle. Let's check it. Nice. By the way, as you know, this program gives new problems every time. It is legitimately true that I may once in a while get one of these wrongs, and we'll work that out when that happens. I don't like to edit that out because I like you guys to see my struggle. Okay, so now let's go on to problem, and that's how you handle a rotation. Let's go on to problem 22. Draw all lines of symmetry for the following figure. Now, all lines of symmetry it means I'm going to draw a line such that I can fold a shape over on itself, and it should be the same. So if I were to draw a line, let's say right here, if I were to fold this side over here, would it line up? No, because it would have a section right here that's not there. So where is this line of symmetry? Well, turns out, oh, I gotta click on the line button. That's what it turns out. Look at that. Could I fold this shape over the line, and would it line exactly up here? Yes, it would. Check that bad boy out. And that's what just a line of symmetry is. We're going to get into 2 other kinds of symmetry here in the next few problems that are a little bit more. We're going to talk about rotational symmetry and point symmetry. So let's first do rotational symmetry, and that is going to be problem, I believe, 23. A regular hexagon is shown below. Suppose that the hexagon is rotated clockwise about its center so that the vertex at N has moved to J. How many degrees does the hexagon rotate? So if we're rotating about its center, that'd be like me sticking something through the center and just rotating it around, right? Well, in this case, we got to do a couple things. Number one, it's a hexagon, so that means it's a six-sided figure, okay? So six-sided. If it has six sides, for me to take M and to rotate it so it moves to N, right? Or I'm moving into J, excuse me. Undo. N first to O, and then I'm going to go O to J. We need to first find out how much is it just to move. So if I were to look at this angle right here, how much is just that angle? And then how much would each angle be, right? Now we know, watch this real quick, I'm doing this on purpose with a mouse though, so be a little forgiving. If I were to connect all these arcs together, they make a circle which is 360 degrees, right? But I want to know what just one of these arcs are. So how many arcs are there? There's 1, 2, 3, 4, 5, 6. Turns out the same number of sides. The number of sides tells us the number of arcs. So I need to divide this by 6 to find out what's just that little arc, which is, what's 360 divided by 6? It's 60 degrees. Okay? So then, if I want to now know, let me get a highlighter out there. I'm going to go with green highlight. If I want to know what's the arc to go from N all the way to J, how many of those 60 degrees I'm doing? I'm doing 1 60 degree, 2 60 degrees. So what's 2 times 60? It's 2 times 60 equals 120. So that means it needs to go through a 120 degree rotation in order to take the vertex N and line it up on the vertex J to rotate it to where it would line up exactly there. So let's take a look at this. 120 is what we said. Let's try it out. Check answer. Boom, look at that. And the last question we're going to go through today is question number 25. Boom. This is talking about two other kinds of symmetry. If we want to see if it has rotational symmetry or if it has point symmetry. Now, rotational symmetry, got a little note for you to look at. Let's go to it because I want you to write this down. Write down rotational symmetry. It means, first of all, we divide by the number of sides if it's a regular figure. And we want to find out if I were to rotate it, can I rotate it less than 60 degrees or less than, uh-oh, my pen. I need a pen that works better. If I were to rotate it less than 360 degrees, will it line up on itself and appear unmoved? Appear unmoved. Anything can rotate 360 degrees and appear unmoved, but I want to know, can I rotate it less than 360 degrees and appear unmoved? For point symmetry, I want to know, is there a line I can draw through it so that when I flip it 180 degrees, rotate it 180 degrees, is there a point so that when I flip it 180 degrees, not a line, I'm in a point, will it line up on itself? So we're going to find that out. Let's take a look. So, first of all, I'm going to tell you, if something has rotational symmetry less than 180 degrees, it should have point symmetry. So let's look. So if I'm going to rotate this thing right here, boom. What are each of these arcs? Remember how many arcs are there? There's 1, 2, 3, 4, 5. So we know we're going to take 360 and divide it by 5, which is going to be what? Well, this thing's in the way. There we go. 5 goes into 36. 7 times is 35, leaving 1 0, so it's going to be 72 degrees. So I know that every time I rotate it 72 degrees, these vertexes are going to move on to each other, which makes it look like it's unmoved. So yes, it has rotational symmetry at an angle of 72 degrees. Does it have point symmetry? Well, it'd have to be able to flip 180 degrees. Remember I said that? The only way it flips 180 degrees is if we can multiply 72 times something and get exactly 180 degrees. Well, let's find out. Divide both sides by 72. I'm going to do that math right here. I'm doing it on my phone. What do we get? 180 divided by 72 equals 2.5. Nope, there's no whole number. It can just rotate. It has to only half rotate. So because of that, no, that's not going to have rotational symmetry. So let's see what we got so far. Yet, or not point symmetry. Yes, it has rotational symmetry of 72 degrees, but no, it does not have point symmetry because it's not going to just rotate onto itself going to 180 degrees. It's going to be off. It'd have to only rotate 2.5 times. So let's look at this one right here. Does it have point symmetry? Well, let's find out. Let me get my little thing. I'm going to actually connect these right here. Kind of connect into a box, don't they? And let's see. Those are almost like my lines to the center. So if it's a four-sided figure, what's 360 divided by 4? It equals 90 degrees. Boom. So yeah, that has rotational symmetry because if I rotate it 90 degrees, it's going to line up on itself. But here's another cool thing. What's 90x equals 180? Let's see if it can rotate 180 degrees exactly. Well, divide both sides by 90. And we get that x equals 2. Boom, it goes in there perfectly with its rotation. So every time I rotate it, if I rotate it 180 degrees, it's going to look unmoved. So yes, this has point symmetry as well because I can flip it 180 degrees and it will line up on itself exactly, a whole number. Whereas this one was 2.5 when we divided it. It's not going to work, okay? So that is some examples. So let's put that in there. Yes, it has rotational symmetry of what? 90 degrees. And yes, it has point symmetry. Let's check our answer, and boom! Does anybody see why I'm partially correct? Because I accidentally put yes on the point symmetry there when I should have said no. I was saying no in words, but I put yes there. So let's recheck that. I was like, what did I do here? I had to have done that right. Let's try that again. There we go. Because this did not have point symmetry. I said it. I just put yes. You got to watch them clicks. I do it too. All right, guys, that's it. Have a great math day. Transform. Peace out.